Okay. So, but I mean, so we are in the middle of discussing regression. That's chapter 11. And last time I told you about what regression problem is, and then what's so special about the regression problem. Quick review. So last time, talk about regression problem. What is so special about it? And what I said is there's a special thing about regression is that target domain Y has a structure, which is, in this case, is a distance, in our case. And the typical, most of the time, we're going to use R as a subset of real number. This distance really means if we have a two elements in Y, we can subtract it and take an absolute value. So that gives us the distance between these two elements. And then in the regression problem, risk what error, which really tells us what we are really looking for. Consider this structure. So when we measure an error of an output of a hypothesis, instead of saying we give a number 1, if we give 1 if they are different, otherwise 0, that's the kind of error we use for classification. In the case of regression, we use a typical example is something like we compute a squared error, where even though h of x is not exactly the same as y, if it's close to y, we in a sense score high. If it's far from y, we penalize a lot. Okay. So that's the idea of regression. And that regression problem, actually, although I don't give you any examples about it, it appears quite a lot in practice. And even when you use the most modern technologies like neural nets, at the end of the day, you often solve classification problem and regression problem. So whatever you learn today is going to be relevant in that context as well. And also we talked about some generalization bounds. For regressions. And then we discussed two bounds. One is based on the finite hypothesis set. And the other was, it cannot be applied for infinite hypothesis set, but that uses Rademacher complexity. So, okay. So what we're going to cover today. And then also the two more lectures in the next week and a week later are going to be about some concrete algorithms. So today we will talk about some very basic algorithm called linear regression. And then we also talk about kernel-rich regression. So you can ignore the kernel and you can just also say it's a rich regression. So linear regression is, I'm going to tell you soon, but it's very much like empirical risk minimization that we talked about. So it just tries to optimize an error, empirical error, which is defined in our context in terms of this R, which is means the squared error or some other things. So it doesn't have any terms which try to minimize the complexity of the model. Kernel-rich regression or just rich regression is empirical risk minimization plus some regularization. So then this regularization is try to minimize the complexity of the model that the algorithm come up with. And then in this specific case, they try to minimize the L2 norms. So it's a squared norms in the second algorithm. Okay. So let's start with this corner-rich regression. No, not corner-rich regression, linear regression. So, I mean, the linear regression can be explained in a multiple different way, but in our context, what it really tried to do ultimately is that, I mean, we have a bunch of the input-output pairs. And then from this input-output pairs, which are in the so input-output pairs, we want to come up with some function f that goes from x to y. Let's write it h, such that it interpolates this x, y well. So that's one purpose. The other purpose is I mean, maybe that's more important purpose is that we believe this S is really coming from example. There are examples drawn independently from some distributions, which we don't really know. And then we want to come up with H, which has a minimum errors with respect to that distributions, which specifies the input-output pair, appropriate input-output pairs. Okay. So coming up with, something that has a good generalization error. That is problem that we want to solve with using linear regression. And linear regression approaches this problem by formulating some hypothesis set and specific optimization objective and solve that optimization. And the hypothesis set linear regression uses is a linear functions. So we're using some feature. So it's we consider a map that maps x to some real number, right? And then that real number is given like this. It's an inner product of w and the phi of x plus some bias term b. So where v, okay, so x and not x, w here is an element in some n, it's a vector in capital N dimensional space. V is a real number. And where phi is a feature map, which is defined as a mapping from x to r to the n. So we encode each input using feature map phi, and then that will map each input into some the high dimensional space r to the n, maybe high dimension or low dimension, but the feature space r to the n, and we compute then we compute some linear functions there. Okay, so that's our hypothesis, and using that hypothesis, the goal is to find one function h that that has a good generalization error. And to do so, linear regression solve the following optimization problem. Okay. So for linear regression, input is S that I talked about. And then what it does is that once you give an input S that's given above, it solves the following optimization problem. Maybe write it as more like an algorithm. Find W star, which is max, and write it as a loss of think maybe this is not. Just write it directly. Next, WB, step 1 over M. W of xi b minus yi squared. So that's the optimization problem is solved, and then it return either it returns W star B star directly, or you can return a functions that take input x, and then compute this the quantity that I just drew on the right hand side. So that's the how the linear regression works. And from the using if I use the terminology that I explained to you before, so really what's going on is that this linear regression algorithm is using the following loss function. So this is term here, really coming from empirical risk, empirical error respect to and then hypothesis is this one. It's p of x plus b. But then the empirical error itself is defined in terms of loss function, which compares to y, and then and then it returns the error for y and y prime. In this case, it's just the squared error. So this R head of S is defined. If you call it this one as a function h, R head of S is defined as equal to 1 to m plus functions h of xi, yi. So this is a general form of how we define the empirical loss or empirical error using loss function L. And if we expand the definition, that we get the one here. So sometimes people say linear regression is just finding a good linear function based on mean squared error. That's because if you look at the formula here, the optimization objective is really squared error. You're computing the squared error and taking its mean. So, and then the functions, the hypothesis we are using is a linear functions. So mean squared error plus linear functions. Those two concepts capture the key idea of linear regression. Okay. So then the next question becomes how we solve this linear regression problem. It turns out that solving this linear regression, I'm sure like many of you heard about it in the linear algebra course and so on. So, and then the solution for this linear regression problem actually can be expressed analytically, so that there's an analytic solution for this problem. Then I want to talk about this. So to talk about this, it's convenient to use some matrix notation. So we're gonna use the matrix notation X. Solution. So we're gonna use matrix notation X. That is going to be a matrix where each column talk about each input. Okay, each example. Input of each example. So the first column will be v of x1 together with some extra part which has a number 1. Second column will have v of x2, which also have an extra row, extra entry, which has a number 1 and so on. And we have m examples. So the last one is v of xm, and then there's 1 here. And then dimension of this matrix is going to be n plus 1 times m. Okay. And then we will introduce another matrix y, which will be board a bit larger. Yeah, so y, which will be just column vector, where the target value will be just listed from the top to the bottom. Okay. And then we write matrix W, which is also a column vector. And then this column vector has W1 up to Wn, but there's one extra thing, which is B here. So once you write it like this, now we can write this optimization objective as follows. So we can write it this way. Objective can be, I will just write it as just objective instead of argmax, max over all W, where we are maximizing f of W. Then what I mean by f is the following. So 1 over m. And then we are subtracting two vectors and then take this L2 norms. What we compute is X transpose and W. They will correspond to this quantity minus y and squared. Okay. So the X transpose W is a vector, with y is another vector. If we subtract the vector and then compute its L2 norm, which means that we square each component of the vector, add all of them together, and then take a square root. But because of this square term on the outside, I mean, square root just disappears. If we do so, these two objectives are exactly the same. They say exactly the same thing. Just here we are using matrix notation to, should express things a bit simpler. But once you do so, we can immediately see that what we are trying to solve is essentially a kind of simple optimization problem. This is a quadratic function. Yellow. The function we have here is a quadratic function. It's a bit like some ax minus y squared, okay? So it's a simple quadratic function, especially it's something called the convex function. And furthermore, this function is differentiable. So what we can say is that this f of w has an optimal value, it has a global optimum when the derivative has a global optimum, and also the global optimum is obtained when the derivative of f is equal to 0. So if we compute the derivative, then although it's matrix, things behave very much like everything is a scalar. So if that computing the derivative is something very similar to what you already know, except that we have to be a bit careful about matrix, essentially what you already know. So like computing the derivative of a polynomial. So then this has to be 0. So global optimum holds when the following equation is true. So where we are. So we said here's a linear regression problem has tried to solve some specific optimization, which is minimize mean squared error. And because the objective is really nice, it's a quadratic convex functions. We can find the optimal value. The optimal value is, we know where optimal value is obtained. And then actually the place where optimal value happens is when the derivative is equal to 0. And by computing derivative is equal to 0, we get this formula. Okay. So let's So then now the next question is how we can simplify the formula. From there, how we can get value of W. This is one. And then when the simple case is if X transpose is invertible, then it's quite simple. You just take an inverse of XX transpose there. So that W go to XX transpose inverse X and Y. So that's a simple case, and perhaps you know this case already. But suppose XX transpose is not invertible. So what should we do? So then you may ask, okay, is there a solution in this case? And if there's a solution, can we characterize all the solutions? And also if there are many solutions, is there any way to find, is there any good criteria to choose one out of all those solutions? So I think maybe it's good for you to think, for number one, I think it's simple, so perhaps everybody knows about up to number one. Perhaps also everybody knows about number two, but I want to give you maybe 2 minutes to think about how you can handle the second case where XX transpose is not invertible. So think about it, and then maybe you can write down the general form of all the solutions, and maybe you can convince yourself why that is the case, and also you can say which one you want to pick out of all the possible solutions. So by the way, there's some particular problem that I mentioned to you in like before my lecture, some projects that I have been doing with my students. Actually, it falls in that case, we also have to solve this. Yeah, you have to use a pseudo inverse, but I want to come up with some good explanation. So it falls into number two case. It was the matrix was invertible, but it was very, it's very degenerate. So it's very close to the non-invertible case. So we have to use something like number two. Okay, so let me tell you the answer. For if it's not invertible, then the general solution will have this form. W will be, as the Simon said, we have to use pseudo inverse. I'm gonna tell you what it is. And XY, but that is not the only solution. All the solutions are of this form. dagger transpose and W0, where W0 is any vector of size n+1. So this is the solution. Okay, and now so what is pseudo inverse here? Some of you already know, maybe not all of you knows about this. Pseudo inverse is so if you have a matrix A, then pseudo inverse is the unique matrix that satisfies the following condition, which always exists. It satisfies the 4 conditions. The first condition is condition 1, say that if you have A transpose, A pseudo inverse A, that's the same as A. Second condition is A pseudo inverse A pseudo inverse is equal to A pseudo inverse. So it's not quite computing the inverse, but I mean, if you do actually have one more term like A or A plus, A pseudo inverse in the first or second equation, then you have something close to the inverse operation. And the other 2 things is that A pseudo inverse A is a symmetric. So if you take a transpose, same as this, and then other directions too, pseudo inverse. Transpose is equal to A transpose. So then we may ask, in our context, so what is this pseudo inverse? So I mean, in general, pseudo inverse can be computed by taking singular value decompositions and then taking, so just take the reciprocal, so if 1 over something for every singular values. So that will give a pseudo inverse. But in our context, because XX transpose is a symmetric and it's a reasonably nice matrix, we can have a much kind of more concrete feel about what pseudo inverse actually is. So if you for XX transpose case, we can think about the Eigen decompositions. So Eigen, we have the orthonormal matrix, which consists of eigenvector, then eigenvalue, and then transpose of this orthonormal matrix. And because this XX transpose is actually a symmetric and positive semi-definite. So this is, this notion of positive semi-definite is the one that we used for corners when you define corners. So it's a positive semi-definite. That implies these eigenvalues are all real and non-negative real. So then how can we compute pseudo inverse? Transpose. Pseudo inverse is the same view, but we take, in instance, the inverse of sigma whenever some entry is not equal to 0. Okay, so that's what this sigma dagger say. The sigma dagger is a diagonal matrix such that sigma ii, so 1 over sigma ii, if sigma ii is not equal to 0, otherwise 0. Sigma ii is always greater than equal to 0, and then we essentially take an inverse if possible. So that becomes a pseudo inverse in this case. Now, based on this knowledge, so here's one thing that we can easily check, which is that we can show this W times this equation is true. So let's do that calculation here. Then I will tell you, okay, what's really going on here. Let's first do the calculation. we do the calculation. It's a X transpose W is that X transpose X transpose dagger XY plus X transpose. I mean, just write all the step. Identity matrix transpose dagger transpose W0. Then we can simplify the second term a little bit. So identity matrix, the XX transpose identity matrix is just XX transpose. And then the other term will be XX transpose. So then you can immediately see we are in this, in this case. So we say A transpose A is the same as A. So we have, that kind of situation here, and that's going to be the same as the one before. So the second term will disappear. So that shows, so this term will disappear. And then if you continue the calculation, we have, and we have to deal with the first term, but here we are using a few more facts about the pseudo inverse. So if you have multiply two matrices and take a pseudo inverse, it behaves very much like an inverse. You know what I mean? So it's transpose. So it's we swap the order of the matrix and then we take a pseudo inverse each. So that's the same as what we, so that's the same as what we can have. But it's like there's some inverse operation, and then also the pseudo inverse and transpose commute. So it's transpose X. Now what we can do is we group these two guys together. X. So we have X transpose X and Y. But then, one of the properties about pseudo inverse, say this one, this, the A transpose A is a symmetric, and the A pseudo inverse of A multiplied by A is a symmetric. So this one, the transpose operator will disappear. So that will give us X transpose X pseudo inverse X pseudo inverse X of 1. So now we use the, this is what I highlighted as a yellow again. So you can see that, this is the same as X by yellow things that I showed you above. So it's the same as X. And then the remaining part will also the same as X because of the same reason. And that will let us prove this is what we wanted to prove, which is say that X1. So that shows, at least what I wrote in one, everything what W of the form is going to be a solution. But then you may ask, okay, it looks like it's just all of them are solution. And for one question is, are they going to cover all the possible solutions? And then second, can we get some intuitions about it? Because some intuition about it can help us to say, if you suppose that you are supposed to choose one out of all the solutions in number one, so how are you going to choose it? So if you have a good intuitions, then that intuition will guide you to make the right choice. So what really happens in number one, and that's the reason I talk about this, Eigen Decomposition, is that, so I don't know, maybe how, might or might not have forgotten about this from the linear algebra course. If you have an Eigen decomposition, so U is a bunch of eigenvectors. U1. So dimension, I think. So it's so the X is a n plus 1. Right. So it's an n plus 1. So there's an n plus 1. So there are n plus 1 eigenvectors. They are all, they normalize, they are all orthonormal vectors among each other. And then one thing we know is that any vector like W can be decomposed into, this W, U1 and U n minus n plus 1 acts a bit like a unit vectors. So they can provide a new coordinate. So we can replace so any weights, which may or may not be a solution of the equation that we are talking about, can be expressed as A1, U1, A2, U2, so on. So A n plus 1 and U n plus 1. So then, so suppose that for this sigma is written such a way that all the non-zero values, eigenvalues are, above. So say there are k non-zero eigenvalues, and then zero eigenvalues happens later. Okay. So if that's the case, so then so if sigma is written in the case, the eigenvectors that correspond to this zero eigenvalues will happen in the later part. And one thing that happens when you, okay, so that's the situations. Now what this solution, the form in number one, say is that its first part talk about what should be the values of this A1 up to AK for eigenvectors whose eigenvalues are non-zero. This is the second part. Tells us what should be the values for AK plus 1 up to AN plus 1. Okay. So they first provides, so the first provide informations about the components whose for which the corresponding eigenvalues are non-zero. The second provide informations about the components for which the corresponding eigenvalues are zero. Okay. So okay. So now from these equations, so that's the kind of the overall picture about this W. And then now what this equation really tells us is that now, although I'm not going to give the calculation, if you do the calculation of X transpose multiplied with W, what happened is that this A1 up to AK get increased by the eigenvector. All of them are increased by increased by a factor of the eigenvalue. So it becomes lambda 1, 2, lambda 2, lambda n plus 1, which means that because lambda n plus 1 or lambda k plus 1, they are 0, this extra term, when you multiply with X transpose, it will become 0. It will just disappear. Okay. So whatever value they have, they all disappears. Okay. So what that means is, as far as solution is concerned, this green part can be anything. And then this, so that's why, I mean, this that's the green component, we have W0. That is selected as an arbitrary vector. So when you select the arbitrary vector, if you compute, multiply with it with this I minus XX transpose, the pseudo inverse XX transpose, that will only select, I mean, the components corresponding to, I mean, this zero eigenvalue eigenvectors. So this green part covers the green part that I wrote there. Because our equations doesn't say anything about the green part, that can be anything. And then for the remaining part, I mean, this one provide say that has to be exactly the same as x times 1. I mean, again, I'm not going to tell you about, like, go through the details, but the point I try to make is that, I mean, the form of W is really say, I mean, how W should look like from the eigenvectors for non-zero eigenvalues and eigenvectors for zero eigenvalues. So it have that kind of decomposition. For the second part, it doesn't impose anything. For first part, it imposes conditions based on the equation that we want to establish. Okay, so this is not a proof, but I hope it gives you some intuition. So now let's think about the following question. So suppose we want to pick solution W. Okay. So solution W. Sorry. So suppose we want to pick solution W, that whose norm is minimum. Okay, so how should we pick? And for solution W, okay, one thing we know is that, I mean, if, you know, because I said for this green part, we can choose anything. In order to minimize its size, the best option we can choose is that for green part, we just pick 0. Okay, for the red part, we have to, I mean, there are specific choices we have to make. So the one way to achieve the solution with minimum size is going to be set the green part to be 0. That corresponds to setting this W0 to be equal to 0. So the solution that I wrote too many, so maybe just write it 6 here. So minimum size W. What is it? I mean, the minimum size of W is going to be what Sam said in the beginning, which is just take a pseudo inverse and take it one. And that has the minimum size. That's because it essentially amounts to saying for all the extra components who are like some flexible component like the green one that I told you here, we're gonna set all those coordinates to be equal to 0. So in practice, what people use quite a bit is that, see what other colors I have. What people use quite a bit is, I mean, these solutions and then this solution. So in invertible case, people use the one that I wrote on the top. In the non-invertible case, people use the one below. But for some of your application, maybe pseudo inverse with a minimum W, minimum size, maybe not so ideal. So then you may go back to the general solutions and try to come up with something that perhaps behave a bit better. Okay, so that's overview. I mean, that's I think almost the end of the linear regression. So linear regression, it tried to minimize mean squared error, and it turns out that optimization objective have its solution can be analyzed analytically. If XX transpose is invertible, we can have there's a unique solution which we can compute by applying the matrix inverse. Otherwise, there are lots of solutions, and you can choose one. I mean, then the solutions can be understood in terms of Eigen decomposition, and then based on that understanding, you can choose the minimum or something else depending on your needs. Okay. Now, so it looks very nice because it's have an analytic solution and so on. But if you use this in practice, there are some problems. 5, 6. So there is a problem, which is that it doesn't generalize well. So actually, you can get an idea about why that is the case. I mean, when we study the classification, we talk about the so-called empirical risk minimization, which try to minimize empirical error. I mean, this algorithm is really minimizing on empirical error. So we learned something similar ERM, and we found that that's not so ideal because it doesn't really control the model complexity. In other words, whatever, I mean, we are doing best in terms of sample, but so we are doing best in terms of sample S in both cases, but that doesn't necessarily means we are doing best in terms of our ultimate goal, which is in the case of classification, it was a risk or generalization error. The same, we have a loss or generalization error for the classification. The same problem happens. So what should we do? So that leads us to all the other algorithms that I'm going to tell you. So we're going to study 3 algorithms. One is the rich regression and its kernelized version. And also we're going to look at the support vector regression, which is a bit similar to the idea of support vector machine. And then the last is going to be the lasso algorithm, which is a different type of regularization. Okay, so let's look at the kernel-rich regression. And then actually to see where this kernel-rich regression comes from, then, I mean, I don't know whether this is the ideal way to look at it, but we can look at, but there's one way to see some motivation of kernel-rich regression, or some rationale behind why people study kernel-rich regression is to think about some of the following theorem, which tell us about generalization. Theorem 11.11. The theorem says the following. It says, suppose we have a PDS kernel. And say H and the phi are the RKHS and the feature map of phi of K. So we make some assumptions that perhaps use also a hypothesis set. We are thinking about mapping that maps input X to inner products W. So it's a linear function, but in RKHS, using RKHS. So then we assume that the norm, because the norm in this RKHS is bounded by lambda. What is this norm? Norm is square root of inner products in RKHS. And this is quite important. It's bounded by lambda. And we also make some assumptions about input and loss. So we say there exists some R and M such that for all the inputs, bounded by r squared or x and x. I mean, this is not an unrealistic assumption. That's because we can normalize kernels, because I mean normalization is one of the things that we can apply to the kernel. If we do so, we can make kxx bounded by 1. So this is not an unrealistic assumption. And then the second one is quite strong. Second assumption said loss is bounded. In this specific case, we care about squared loss, so we bound distance of h of x and y to be bounded by m for all x and y and h. Okay. So h is from hypothesis set, and x is from x, y is from y. Okay, if that is the case, then for any learning problem, any required precision, we have the following generalization bounds. So, I mean, something that you see have seen over and over again, say that for all hypothesis, each error with the means, the error is computed using this squared loss. So it's computed with squared loss. It's bounded by corresponding empirical error plus 4m square 2m log 1 over delta with high probability. So this is our average squared error. So the average squared error is bounded above by empirical, the squared error, mean squared error. So empirical squared error means that the mean squared error plus some extra terms, and then these two terms have this form. The first is related to the Rademacher complexity, the complexity of the hypothesis set. Second one is related to the desired precision level, like delta. So this is some general theorem that's true, and then there's some other versions where these two terms are, so that there's a second term that you see here. It doesn't say anything about the sample, but we can, let's not worry about this second version. Okay. So this theorem is actually an easy consequence to what we learned before. So we learned the last time some theorem called, so this is an easy consequence of theorem 11.3 that we learned, and theorem 6.12. So why that is the case? So theorem 11.3 tells us the following. We say we have something like this, except that at that time theorem 11.3 say it's a 2 times mu and Rademacher complexity of hypothesis set H plus the bound on the loss function, but in that case, our loss function is a square of this difference, h of x minus y. So the bound is going to be m squared. And because our loss is a squared error. So this will be, our theorem will say this is same, m squared to m 1 log log 1 over delta. So that's what the theorem 11.3 tells us what it means, the generalization bound in this context. But then what we have to do, we have to replace this mu, which is the Lipschitz constants of our loss function, and then the Rademacher complexity. And then Lipschitz constants, our loss function is this guy. Let's just change the color to the green. So now what we do is we're gonna use this theorem 6.12. Theorem 6.12 tells us if we have a bounds on the weights in our linear function, also all the inputs are bound by r squared. So then that theorem say the Rademacher complexity, this part, is going to be bounded by r squared, gamma squared, and then. So we got the term on the right-hand side. So the only thing that remains is how we can change this mu. And what is mu? Mu is a Lipschitz constant for our loss function, which is a square. I mean, the squared error. So that was. So, and then the Lipschitz constant, when we talk about Lipschitz constant, we fix the second component, only vary the first component. And then Lipschitz constant is essentially an upper bound on the derivative. So if you take the derivative, then that's going to be L y is going to be 2 y prime. But what we do know is that this, I mean, the possible y, I didn't really say it this way, but you can also say y prime. It's bounded by m. So that the condition, this bound condition on the loss, let's say that this Lipschitz constant is bounded by 2 times of m. So that's why we have this number 4m. So 2 is coming from original theorems, then the other 2 is coming from the Lipschitz constant. So the theorem is an easy consequence of theorem 11.3 and theorem 6.12. Okay, but what the theorem really tells us, the theorem tells us is the following. We say, if we want to have a good generalization bound, it may be good. I mean, one kind of any theorem within using Rademacher complexity says that to get a good performing algorithm, try to find some mechanism to control the Rademacher complexity. Okay. And in this case, Rademacher complexity is directly related to the size of the norm. So one good approach is try to minimize the size of the norm. Okay, that will give us. I mean, we try to minimize both the empirical error that's coming from this this term, as well as size of the norm. So then that will give us some good mechanisms. I mean, maybe give us a good kind of alternative algorithm that may generalize much better than simple linear regression. So that's the idea behind the corner-rich regression. The idea is it tried to minimize both W, I mean, this norm of W in RKHS, and then this the empirical error at the same time. So let me tell you this algorithm, and then analyze a little bit the primer form, then that will perhaps take all of our time. So before actually going to the corner, we can talk about maybe the better way is just a rich regression algorithm. Let's just say corner-rich regression because it's not corneralized, but we are using features of corner. So the one first, let's think about the primal form. So how did this algorithm is defined in its so-called primal form? The algorithm is defined like this. It's like before input of the algorithm is sequence of input-output pairs. And then what does the algorithm do? It solves following optimization problem. So then so there's optimization objective f of w, and then where f of is defined like this. It's a combination of lambda w square plus summation of m. So we are not taking 1 over m. That's because, in a sense, 1 over m is kind of swallowed by this lambda. P of xi. And also, we are not thinking about bias term here. Square. It's very similar to the linear regression. And there are slight differences here and there, but the key difference is the introduction of this new term. So it tries to minimize the size of w. So just like before, we can kind of express this as a matrix form. So this is root square plus this is just computing x transpose w minus 1 squared. So here x is a bit different from the one that you see before. Here we just say v of x1 to v of xn. Okay. So then once we compute the solution, we return it. Either we can return w star, or we can return a function that maps x to v of x. So we have either one or the second. But just like before, it turns out this primal form actually have an analytic solution. And furthermore, we had to worry about non-invertibility and use a pseudo inverse and so on. But in this case, by the way, lambda is always some constant hyperparameter, some constant which is fixed and greater than 0, and it tells us how much emphasis we want to put the reduction of model complexity. That's how much we want. Like we regard this size of W as important in comparison with the empirical error. But it turns out if we do so, then we have an analytic solution. And then actually the analytic solution is much simpler than linear regression because we don't encounter this non-invertible case. Okay, so try to see this. So the first thing we can notice is that just like before, f of w, it's a convex differentiable function. So it attains a global minimum. And furthermore, it happens if and only if derivative of f is equal to 0. So we compute the derivative. We compute the derivative, we have to lambda w plus derivative in this matrix form. So then we get 2 times x transpose w minus y. And we want to say this is equal to 0. Now, if you simplify a little bit, this means that we have lambda identity matrix plus x transpose w is equal to x of y. That's equivalent to like this. So at this point, we say, okay, we might think that, okay, just like before, we have to do case analysis on on the invertibility of this matrix, and if it's not invertible, we use pseudo inverse and so on. But it turns out that's not the case. And then the reason is this matrix is always invertible. So why is that the case? I mean, the reason is now think about its eigenvalues. Values of this matrix, lambda I plus XX transpose. Then its eigenvalues are the sum of, because the first matrix is identity matrix, this eigenvalue is a sum of lambda plus eigenvalues of XX transpose. But when I talk about linear regression, I said eigenvalues of XX transpose, they are always non-negative. So they are always real number, non-negative real number. And the lambda is a positive number, which means that all eigenvalues of lambda I plus XX transpose are positive. Now, one thing that we do know, or maybe you forgot, but one thing is true, that the determinant of lambda I plus, I think it's true, but if I'm wrong, please correct me. Okay, I think some of you are perhaps more familiar with linear algebra than me. It's the products. I think it's a product or sum of eigenvalues. I forgot exactly. Lambda I plus XX transpose. But the products or sum of all the positive eigenvalues, there's going to be positive, so it's going to be positive, non-negative. So that means determinant is not equal to 0. That means it's invertible. Okay, so that's why this invertibility is guaranteed automatically. So from here, we can derive a solution, and the solution is going to be W lambda I plus XX transpose inverse x1. And sometimes, so that's the solutions of the rich regression problem. So we have about 5 more minutes. I say a few words about this, and then maybe we finish early today. Because the next part is going to be a dualization, which will require a lot more time, much more time than 5 minutes. So sometimes when people look at, in machine learning, when you encounter some problems where you have to compute the inverse, then sometimes the people say, oh, if the matrix is, it's not very good, so it's very close to singular, so it's very close to non-invertible, then people say, oh, just add this lambda, very small, add identity matrix multiplied with very small constants. Okay. So, okay, that's a kind of more like viewed as some form of engineering trick that people use to make matrix a bit nicer, so that all the computation will go through. But if you look at these derivations in the primal form, they really amount to saying you are adding some regularizer somewhere in the original formulation. Especially you are adding this L2 regularizer, which I used here. So just be aware of this. You can view this adding this lambda I as some kind of implementation tricks that make certain matrices stable, but that's also often corresponds to you are changing your optimization objective in your machine learning problem by adding this extra regularizer. Okay, so that's it for today, and next month, Tuesday, we will we'll finish off this rich regression and talk a little bit about this support vector regression. And next Thursday, we are not going to have any lecture because, I mean, that's the undergrad interview period, and all the lectures are supposed to be canceled. Okay, so thank you very much, and that's it for today.